Huh? Oh no, you can't see. There we go. So since we're now expert in implementing our own solvers, so the ideas of taking information from the local environment of a particular root, like probing its inclination, can be extended further. Here, for example, for the second method. So we say that the next point is the information at the current point, like position and function value, including what we actually know from the previous point. So we now have 3 points to consider. The current one, the previous one, and the next one. So finding these finding roots with different approaches can be, well, just beneficial to have more tools at hand in case one of your tools does not work. There always could be an instability in the numerics of your solver. Then you could use another solver. You could hit limits in your computational power or your storage on the computer. Then you choose a different solver. Well, speed is a concern for you. So there are many different solvers, but they all follow a certain idea that can be put into formulas and that is, let's say, promising on finding roots, right? Promising in finding roots of a function. Now, there are very, very smart people who have done a lot of work in developing algorithms, implementing them, testing them, comparing them, and the best of the best is available for us, free to use. So we can, for example, use SciPy, and it comes with already a bisection method. It comes already with a Newton method. It comes with other solvers as well. So after we have seen in the first part of the lecture how these algorithms work, by implementing them ourselves, or actually see the implementation ourselves, implementation was done before, we now use a package of Python and see how we invoke these functions. Invoke means here how to use. So of course we need to first import SciPy, and the bisection method as well as the Newton method actually are part of a submodule that is optimize. Right, when we have loaded this, we can basically call the bisection method as optimize.bisect. Now the simplified syntax is given here in the middle of the slide. Bisect takes 3 arguments. One is the function we want to optimize. A is the start of the interval, right? And the interval is between A and B, including A and B. And the third argument is B, the end of the interval. Be very, very careful. You cannot just blindly use any number here. You must have a good guess where the root of the function could be. For example, my favorite function today is x squared. So I put in here x squared. And for A, I put in minus 2000. And for B, I put in minus 100. Will I find the root of x squared? Yes or no? And why? Do you have any guesses? Are you following what I want from you? I have x squared, right? X squared. That's my function. I want to know the root of x squared. I want to use the bisect method. Bisection in optimized from SciPy. A, I set minus 1000. B, I set minus 100. Will I find the root? No, I will not, because we already know how the bisection method works. It looks for a change of sign at the middle point. I will not get this. So we must be clever. We must have a good guess where the root could be. So I could say, hey, f is x squared, and I suspect the root to be somewhere between minus 100 and plus 100. Will this work? We don't really have a change of sign, no? Like, remember how it works? It takes the middle, right? And then the function value is 100 is 10,000. The other function value is also 10,000. And at the middle point, I get 0, right? Now 0 is technically plus and minus 0. But with our previous implementation, I don't think it actually will work. Okay, so now there are other functions as well. We always could test it with our e to the power of x shifted down 2 units. That actually should work. And if you look carefully, the example on which we call or test optimize bisect from the SciPy module is actually that function. And I know this because I use lambda. A lot of mosquitoes today, no? I use lambda. I remember lambda. Lambda is used to define a function without giving it a name. The variable is x. The expression is e to the power of x minus 2. My start of my search interval is minus 2, and the end of my search interval is plus 2. Right? So here's the interval again. Here's the expression, and then here's the variable. And when I called bisect method here, I actually get a result. The root 0.693144718. What do you know about the bisection method? Do you remember? So the bisection method was supposed to give you an interval, no? Let's study this a little bit. This is very, very interesting now. So I call this function. Does it do what it's supposed to do? That's the first question. Maybe I just trick you in my slides. Always could be, right? So if you check the documentation, it tells you here the return value is the float 0 of f between a and b. So that is the point between a and b. Now let's see. We have one. Can I scroll up here in the documentation? Is that possible? So we can change this a little bit. You can have one additional optional argument. Full output. Oh, very good. So we only have 41 iterations to get the root. We get the convergence. Yes, very nice. Let's study a little bit more how this function is actually operating, because we should be able to set a tolerance. Very good. So the tolerance is here given to be 2 times 10 to the power of minus 12. Let's put it minus 4 we had recently, right? So you see less accuracy, right, has less iterations. But if we really push it, does it work? Right? 2 times 10 to the power of minus 16 tolerance, we would have 51 iterations. Okay, so far so good, right? Now let's look into the next. Simplified Newton. Again, Newton here is the solver. We had a look how to implement it ourselves. We now look into how to use SciPy to use it. First, we would again from SciPy import optimize, and then from the optimize subpackage, we could call the method Newton. It takes 2 arguments. One is the function we want to look into, and the other one is the starting point of our search. So we would use it here, for example, optimize Newton, give the function we defined earlier, and root guess right is one value. Okay, and again, the root we obtain is fairly similar to the roots we have obtained with the other methods, with the methods we have implemented ourselves. So this all seems to work pretty nicely, right? What else? If they work so nicely, do they work so nicely all the time? Why are there so many different solvers? Well, different solvers again have different benefits. Right. Or the last one, well, let's say like this. So SciPy comes with a lot of different solvers. Right? Not only bisection, not only Newton, there are many, many more. One is Brent Q, right? Without telling you the details about this algorithm, what do we see here? We actually see that the syntax of using them is fairly similar. So we have a function to define with a variable, right? We have to have either a start search to provide, or we have to provide an interval of our search. And this is how they generally work. Now, for systems of nonlinear equations, similar to our nonlinear equations themselves, we cannot write general solvers that guarantee to converge, that guarantee to get the correct solutions. Right. Here's an example, also from SymPy Optimize, where we basically have 1, 2 different variables. We try to find the position 0 for the 2 variables, a system of equations. Careful, so this is one equation, and here is the next equation. And with with one of the more general solvers, SymPy is telling us, well, we only find a trivial solution here. Now, how are the solutions of systems of nonlinear equations defined? Well, if you think about systems of equations, the intersections of these nonlinear curves are the roots. So we have one root here at the green star, another one at the green star at -1, and then another root at the green star just before 1. Now, when we try to solve this, we use SciPy again, optimize the F solver, right, the function solver, a very general one. We can provide different starting points. Just now with my Newton solver, I provide my first guess of x. And here with fsolve or Newton from the optimize class in SciPy, it would do the same, right? But when we choose one starting point, how do we know which of the 3 different roots do we actually get? So one more time, important to note is sometimes we have many roots. For example, a general equation, ax cubed plus bx squared plus cx minus d. How many roots can we have? Up to 3, right? But all the algorithms we just discussed only gave us 1. So to find all of the roots of a function that is, well, nonlinear, that can be a little bit challenging. And what? Suppose I give you something that looks a little bit difficult here. Let's see, where is it? Function f2. I lost it again. F2. Plug it into Newton or bisection method. How do you know that you really get all of the crossings? That's a little bit difficult. So, we tested here on one example. So we have 2 nonlinear equations defined. We plot them. We know where are the roots. What we want to do next is explore how different starting points evolve into different values of our roots. Right? And remember, for each guess, we probably end up with only one root. So here is the example. It's a little bit longer. So we go here. So that's what we do. We plot our 2 functions over here. And we solve them with 3 different starting points. These points I've pre-selected because they give me 3 different roots, right? Visually, I solve the problem, I know 3 different roots. Then I do it in Python, and with these 3 points, the black circles, I get 3 different solutions, the stars, green, blue, and red, or orange. Then I define a NumPy array. from minus 15 to 15, 40 different points, and I do a NumPy array from minus 4 to 3, 4 different points. And I put them in a nested loop. So I run over them. Right? I take an n and I take a m. And these n and m define a starting point, a guess for x. So far, so good. Remember, I have two different functions, right? They can have two different coordinates in my coordinate space, so I can display this in 2 dimensions as m and n here. This is my guess, and I take the guess as starting point for my function f, which is my solution. My system of nonlinear equations. So I get a solution. I call that sol. Ideally, this solution will be identical to solution 1, given over here, right? This is one of the stars. Solution 2, or solution 3 as defined in line 5 to 7. So far, so good. Then I measure the distance in this third for loop, 4. My solution in solution 1, 2, 3, 4. What is the distance between S and my solution from line 14? I take the absolute difference and the maximum. And if the maximum is smaller than 1 times 10 to the power of minus 8, I say that, hey, my new solution for my starting point Mn is identical to solution 1, 2, or 3. If it's identical to that solution, I basically mark that point M and N in the color of solution 1 or solution 2 or solution 3. So here. And that is what I get at the end. So I have my grid of M values, right, from minus 15 to 15 and N values from minus 4 to 3. I pick one point. It's the regular space grid, right, with I think 40 points in one direction, and let me see how much was the other, 80 points in the other direction. So I take this point here, right, at 15 at minus 4, 15. I say this is my guess to solve my system of nonlinear equations. And what I get is the green star. Because here the distance is very small of my solution. And then I say, hey, when you get the green star solution, mark that point green. To the next point, to the next point, and all these points will be green. Okay? So I actually, what do? I do the inner loop first. So that would be, I go from minus 15 to 15, I go up. I go to the next x here, and then I go up again. I get all my green solutions, further, 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 and then I reach this point over here. You see? Do you see this point here? At the bottom, near to minus 2, there are like 5 points that are suddenly red. Huh. So why are they red? When I start with this point, you can try it out yourself, but this point will give you this solution over here, the red star. That's a little bit unexpected, right? If you look at the red point, it's much closer to the green star. But the numerics in the algorithm just works in a way that you end up there. If you look very closely, there are even a few blue points just behind minus 2. Right? The blue point means, hey, starting here brings you to the blue solution, blue star. Okay, after that, as you may expect, a lot of points bring you to the red star. Then there's a region where red and green and blue even mix. That's quite unexpected, actually. Who knows? Right. What else? At 0, there's a lot that doesn't bring you anywhere. There are points missing. Also can happen instability. Solution does not converge. Right, in case the points at 0 are very important to you, you always can try to modify an algorithm. You always can try to choose a different solver. Maybe with a different solver it works, because there are even regions close to 0, 0 where this solver, fsolve from SciPy in its optimized class, we actually get solutions. Okay, but maybe the keynote is the choice of starting point for the solvers can be quite important. It will be very, very difficult to really get all possible solutions for very, very complicated nonlinear equations. And for very, very, it will also be very difficult for systems of complicated nonlinear equations. These are non-standard problems. Right? So expecting a standard solver to do all the thinking for you will not work. You must evaluate very, very critically any solution you get in these situations. Okay, comments, questions? If not, then we can slowly move into chapter 6. And looking at what you are able to do now, right? Writing simple programs, right? Follow the having control over the program flow with conditional statements and loops, converting data structures, data types, solving equations, right? Doing a little bit of linear algebra on quadratic systems, right? Finding the inverse of a matrix, solving systems of linear equations that are fully determined, working with nonlinear equations, finding roots. The next step is into looking how interpolations work, how extrapolations could work, and then how fitting is part of this. And fitting as well as interpolation all kind of go into the realm of rectangular systems. So rectangular systems refer, of course, to systems of equations which are not square. So we will have a matrix that is either underdetermined, or we have a matrix, I should say, system of equation that is underdetermined, or we have a system of equation that is overdetermined. Because fully determined, we know already. So the square system, yes, we've done that already. So yeah, a few questions you can think about. Can we use linear algebra for systems with more unknowns than equations? And again, system here is short for system of equations. How useful is it to have more equations than unknowns? Well, let's say I have just one unknown, x, and I give you 10 different equations. How useful is that? How can we translate these type of problems into Python? And then we have an example. Over here. So here's example. We have a quadratic form. So we have variable constant, variable of linear type and quadratic type. And then we have one equation where they add up to y1. We have another equation where they end up to y2 until we have ym. And m could be a very, very large number, like a million. You would do this, for example, if you have, I don't know, Newton, classical mechanics, you measure the acceleration, speed, and position over time of an object. Right? And with that, you can actually, and maybe they are, or they can be expressed in a quadratic equation where the variable is time. So we could actually measure at many points the behavior and then perform a regression task, a fit. The other example is here. We have 2 equations and 3 unknowns. How do we solve this? Well, we must do some guesses, right? Okay. So on the left side, we have an over-determined system. And on the right side, we have an under-determined system. Yes, so far so good. So what we do next is we look into under-determined systems. The modules we will use are from SciPy, SymPy, NumPy, and Matplotlib. So what can we do with the example given above? Well, we have 3 unknowns and 2 measurements, right? 2 sets of data that we can use. So something will be undetermined, which gives the system its name, the undetermined or underdetermined system. Right. So it's actually quite interesting because most of the decisions you make are with limited knowledge, right? You don't know everything. And the things you can know for certain, well, first of all, there's nothing like this, always comes with a little bit of uncertainty. And then you still need to do a decision. And the best thing you have is to make an educated decision. No? Scientists do this all the time, right? We don't know everything, but we focus on a little bit. We get the information we can get that is useful for us, and within the given limits of our available information, we try to gain some new knowledge that is supported by data, right? Pushing us a little bit forward, limiting the amount of possibilities, making some statements about the connection, correlation, causations. Okay, so back to topic, underdetermined systems. Have you seen that in school? Yes, you have, right? Oh, not on my slides. So for underdetermined systems, we could use SymPy, defining our variables, defining our matrix with the basically information as well as the value vector b, and then provide the expression ax minus b, which equals ax equal b, into our solver from SymPy, and SymPy is clever enough to say, yeah, what you have there is an underdetermined system. So if you give me more information, I could give you a solution, but for now I only can tell you that x is limited to values x3 minus 19 over x, 3, and x2 equals minus, sorry, and my pointer is off, and x2 is minus 3x plus 20 over 3. So we have 15 more minutes where I talk, and then our very talented TA and also our very talented Jenny will tell you some nice Python topics, because the course is ending and I know that you're very tired of me already, which is okay. No reaction. So I do speak the truth. So Python is actually a very nice tool. We are very limited in this course to some very, very basic things, which if you hear them for too long, obviously tires you a lot. So Jenny and Harper will tell you a little bit some nice topics today, right? You speak English or Chinese later?
Maybe in Chinese.
It's okay. Okay. Ask them. They're very nice people, very approachable. Not like me, where you're all a little bit scared. Maybe. So each of them has 20 minutes. Actually, a little bit less, right? Or we have a short break, and after that, there's a teaching survey.
Yes.
20 minutes. And remember, you have to complete the teaching survey. If you don't, you fail the course, which is stupid. Right? So please just complete it. It doesn't really matter what you do there. Well, it mattered what you write there. Of course, it's very important. But for you, right? You want to pass the course, and the only requirement I have is you complete this. So this is very important for you. And it's important for us because it's an EMI course here. So we need to evaluate that this course is taught in English or not. So you can write there that I'm speaking English, and whatever you think of it, it's fine. But right, it's an English course. It's very important that your government has feedback. Yeah, this course is really in English, because Harper and Curtis, you're paid, right? They're paid as EMI TAs. Okay. So 13 more minutes. Let's see. How about this? We finish underdetermined systems, and then we do the fun stuff. Okay, and think about, it's supposed to be more interesting than the basic stuff, so it might be more challenging at first, right? Because it will be a lot of information, but it's just there to show you what you actually could do. Well, could start with as well. Okay, so we test now underdetermined systems. We execute. Curtis, you're here for the teaching survey, right? Or you're also presenting? It's not for you, okay. Okay, fine. Works for me. So we execute here, right? And we get our variables. We test what is x. We test what is a. And we get... By the way, are you still doing the exercises? In class, if you want to have the solution, exercise 2 and 3 and whatever, prepare a solution and talk to the TAs. I will complete the solutions for exercise 1 on YouTube, but the rest you need to work a little bit, right? Is that fine? Yeah, good. Okay, and does it work? This is now the big question. Oh, it works. Fantastic. Any questions? No, right? Easy. So, the system of equation is underdetermined. To find values that do not depend on the variables, we need one more condition. Otherwise, we just have a conditional expression. Also can be useful in some situations, but not all. Okay, if there are no comments or questions, we can do the fun stuff next. And because they are students, it will not be on YouTube.